If you crack open a fresh cocoa pod and pull out one of the raw seeds inside, you won't taste chocolate. You'll taste something intensely bitter, highly astringent, and distinctly unpleasant. It's tempting to assume you can dry and cook this seed to unlock that rich, familiar flavor. But if you put a raw bean straight into an oven, you'll end up with a charred, foul-tasting husk. The signature notes we associate with chocolate, the warm aldehydes and those rich, nutty pyrazines, literally do not exist in the natural plant. We have to build them from scratch. Doing that requires a highly specific chemical sequence. First, a biological breakdown to quietly assemble invisible flavor precursors, followed by a high-heat crucible to trigger their rapid transformation. The final chocolate bar relies on a highly engineered chemical chain reaction, where every single step is entirely dependent on the exact biological conditions of the one that came before it. Long before it reaches a factory, the potential for a bean's final flavor profile is decided on the jungle floor. Packed under banana leaves, the raw cocoa undergoes a strict 3-part biological fermentation. For the first 36 hours, anaerobic yeasts strip away the complex sugars coating the bean. Lactic acid bacteria then multiply, sharply dropping the pH. Finally, acetic acid bacteria take over, triggering an exothermic reaction, driving the temperature past 50 degrees Celsius. This sudden combination of intense heat and severe acidity permeates the hull of the bean, waking up highly specific endogenous enzymes locked inside the seed. These enzymes act like microscopic scissors. They locate massive, flavorless proteins and slice them apart via hydrolysis, leaving behind a loose scattering of hydrophobic amino acids, like leucine. Simultaneously, the internal sucrose is dismantled into smaller, highly reactive reducing sugars. By the time the bean is dried and shipped, it still tastes nothing like chocolate. It is, however, a microscopic trap, perfectly loaded with the exact chemical precursors required for the factory floor. Once those dried beans arrive at the factory, they are fed into massive industrial roasters. This is where the thermal catalyst is applied. Exposing the beans to temperatures between 120 and 140 degrees Celsius forces the remaining moisture out and instantly initiates the Maillard reaction. Under this intense heat, the newly freed reducing sugars from the jungle floor violently collide with the loose hydrophobic amino acids. This high-speed chemical collision triggers Strecker degradation, forcing the atoms to arrange into entirely new, highly stable structures, like aldehydes and pyrazines. Looking at the actual chemical diagram, you can trace the reaction pathway down to the bottom, observing the distinct formation of the pyrazine ring alongside the Strecker aldehyde. These specific pyrazines provide the exact nutty, roasted flavor notes we identify as chocolate. Roasting requires absolute precision. Nudging the temperature even slightly yields a completely different chemical output. Pushing the heat into the upper limits of the Maillard reaction forces the compounds to polymerize into heavy, complex structures called melanoidins. These high molecular weight melanoidins dictate the deep brown color and the distinctly brittle, snappy texture of the finished cocoa bean. The roaster provides the pure thermal energy needed to force those biological precursors to react, turning an invisible chemical potential into an aromatic reality. After the intense chemistry of the roaster, the production line shifts to pure mechanical refinement. Inside the conching machine, the goal shifts from creating chemical flavors to dictating physical texture. Heavy rollers relentlessly grind and shear the chocolate paste. This friction forces liquid cocoa butter to completely coat every single microscopic solid particle, yielding a perfectly smooth, flowing viscosity. The intense friction from this constant grinding also generates enough heat to slowly evaporate away the harsh, volatile acids, like acetic acid, left over from the fermentation pile. Tracing the process backward reveals an absolute unbroken dependency. If a farmer rushes the fermentation phase and pulls the beans from the pile too early, the internal enzymes never activate. The amino acids remain trapped inside massive proteins, guaranteeing the Maillard reaction inside the roaster will fail before it even begins. When you bite into a perfectly tempered piece of chocolate, you are experiencing the flawless culmination of yeast metabolism, enzymatic hydrolysis, and thermodynamics, all functioning in perfect sequence.